Good afternoon, everyone. Good afternoon, courses. So today my defense title is Advanced Localization Approach for Indoor Localization Tracking and Navigation using Deep Learning Techniques. So here during the presentation, first I will discuss about my problem statement and the contributions from the thesis and introduction about this research area. And in this thesis, we proposed uh, five approaches. So first we started with the IMU sensor based localization, and we considered Wi-Fi RSSI based localization. Then sensor fusion. In that sensor fusion framework, we combined IMU sensor data and Wi-Fi RSSI data together to improve the performance of localization. And also we consider camera sensor, and finally to get a centimeter level localization accuracy, we use the UWB based localization system. And finally, I conclude my presentation. So problem statement of this thesis is like improve the indoor localization system performance and reduce the localization error challenges and system scores to get a continuous localization result. To achieve these goals, so when we proposed different localization algorithms, so we started our localization approach using smartphone sensor-based sensors like accelerometer, gyroscope, magnetometer-based sensor data, and identify the user position in indoors. And also next, we also use the Wi-Fi RSSI signals for our localization purpose. And next, to improve the localization performance, we use the sensor fusion framework, which combine the IMU sensor data and Wi-Fi RSSI data together. And also we proposed a hybrid localization system which uses IMU sensor plus camera. So, but the major problem is like privacy issues and processing delay when we introduce camera sensor. And to get a centimeter level localization result, we used UWB based localization system. So here is the research direction. So our goals are like improve the localization performance, reduce the localization error, and reduce the system cost and real-time implementation. So we started with the indoor localization using smartphone sensors. So we achieved the step detection error 3.14% and hedging error 4.72 degree and localization error 0.7 meter. So next, also the very most common and popular localization technology is the Wi-Fi RSSI based localization, and we propose some fusion algorithm to improve the performance and reduce the RSSI challenges. So our system has 0.49 meter error, localization error, as compared to some conventional approaches. And also next, what we did is like we combined RSSI data and IMU sensor data together, a sensor fusion framework. So when we compare the position from both localization, we have the result around 0.42 meter. There is some small increment in the reduce in the localization error. And next also IMU, but to use only the RSSI data, we have some challenges. So also we consider a camera to the system. So using our smartphone camera. So our localization error we achieved 6 centimeter. And to get a very accurate and a centimeter level localization, we use the UWB signal. So UWB based localization we have 7 centimeter. So finally our achievement, we achieved a centimeter level localization accuracy, implemented a real-time system, a real-time localization system which provides continuous localization result, and a low-cost sensors are used. We didn't use any external devices or something. We used our smartphone or a very low-cost IMU sensor or Wi-Fi RSSI signal. And in the case of UWB signals, we simulated the system. So our achievements are this. So here is our publication list. So during this time, we published around 8 papers and Q1 journals and one that were under review. And here around 10 international conferences and 13 domestic conferences. And we have 4 patent application and software registration. So when we start with the indoor localization, the localization divided into building independent and building dependent. So in building independent, we have image-based technologies and dead talking. The networking basically is IoT sensor based technology. And building dependent, we have building infrastructure used, dedicated infrastructure used. So we have Wi-Fi, cellular, Bluetooth based technology, or R5, UWB, infrared, ultrasonic, ZigBee, VLC, visible light communication, or LSTM. So this is we focus on image based technology like a camera based localization, dead blocking, IMU sensor based technology, or localization algorithm, and Wi-Fi RSSI based approach, and also UWB based system. So we start with our indoor localization using smartphone IMU sensor. So we have the proposed system. So here the proposed system, we use the accelerometer, magnetometer, and gyroscope sensors. And from the accelerometer, first we identify the pitch and roll. And from pitch we estimate the step detection, and step length estimation, position estimation. So for the position estimation, we use the heading from magnetometer and gyroscope sensors together, combined using Kalman filter, and we estimate the heading. Finally, we estimate the user position. So the proposed system consists of step length estimation, pitch and roll estimation, heading estimation, position estimation. So to get the step length, we use the following equation, and we use the pitch amplitude. So the conventional system, they use the accelerometer data for step length estimation or step detection. But in our proposed approach, we use the pitch amplitude instead of accelerometer data, and the pitch and rolls are estimated using the equation. And also for heading, we use magnetometer and also gyroscope. So using this equation, we estimated the heading value, and finally the position is estimated using by using the step length and heading information together. So here is the sensor fusion for combining. To estimate the heading, we use the gyroscope and magnetometer. So to combine that sensor data, we use the Kalman filter algorithm. So here is our proposed pitch-based step detector, and a pictorial representation of how the leg during the occurrence of steps, and example of step detection. So the peak is considered as the step. So accuracy comparison, when we compare our proposed pitch-based approach with the peak detection approach, or 0% detection, and also Samsung Health Android application approach. So our approach achieved 3.14% error as compared to other approaches. So here is the heading estimation result. So our proposed heading comparison, what we did, we combined gyroscope and magnetometer data together to reduce the sensor errors. So our proposed approach reached significant improvement in heading error as compared to conventional approaches. So here is the heading error estimation, and also the heading error distribution, cumulative error distribution. We compare our proposed heading approach with the azimuth based approach. In our azimuth based approach means the gyroscope data. Z value of gyroscope data is considered the heading, and also magnetometer based approach. So to validate our approach, we consider 3 experiment scenarios: was rectangular motion, a straight line motion, and a circular motion. So here is the estimated result using our proposed approach, and also we compare with the conventional approach. In the conventional approach, we use accelerometer data for step detection and a normal azimuth heading, like gyroscope Z values as used as a heading value and estimated the position. But in our proposed approach, we combined sensors, like we use the pitch-based estimator for steps, and also magnetometer and gyroscope for heading. And to analyze the result, to validate the result, we estimated the average localization error. And here is the estimated average localization error for 3 scenarios, a conventional method and proposed approach, for 3 scenarios like rectangular motion, straight line motion, and circular motion. Also, we estimated probability distribution of localization error for conventional method and proposed approach for straight line motion and rectangular motion and circular motion. So this table summarizes our entire results. So from the table we can see our proposed method has significant improvement as compared to conventional approaches. And here is our demonstration video. So here this is our basic, the first implemented system using IME sensor. The user is moving and the trajectory pattern is tracking. But this system has some challenges and also some problems. And Next we consider this same IME sensor data with the activity recognition also. It's part of our entire project. So we also identify the user activities and user position. So simultaneously we plot the trajectories. Even this result, the coordinates of the plotting values, so difficult to match with our real scenario. Or the system is only in like a limited scenario. So we next consider some floor map. So we did experiment, we did with a floor map. So we started experiment and we have more accurate or more convenient way of presentation of our result. So here we consider the tables and everything with a floor map. So the results are far better or more convenient to the audience. And next, we also tried multi-user activities, but this system is not that much accurate because our proposed system depends on user height, step length. So this result like depends on each person. Their step length is different, the height is different, and the way they are walking is also very important. So we have some result, but it's very difficult to balance or compare the both persons' position values. But when we repeated the scenario, the trajectory is matching, but after some times later, due to the errors from the sensor, like accumulator error or gyroscope drift error, the performance is going down. So here is our final result. Like we, instead of external lighting sensor, we use smartphone, and we estimated these are the sensor we used for our localization, and we plotted the activity and location values for different activities. So when we consider the IMU sensor based localization, the major issues like IMU sensor accumulator error from accelerometer, gyroscope drift error, external magnetic field affects our system, and smartphone, when we use smartphone posture issues, smartphone swinging motion, and the heading issues and text message or code in the smartphone also affect the performance of the system. And data transmission speed from sensor. When we transmit the data from IMU to the server, there is some issues. And type of user motion, gender difference, and user height difference. So we next check the possibility of Wi-Fi RSSI signal for our indoor localization. So most of the indoors these days access points are very common in everywhere. So we proposed a fusion algorithm using RSSI. So conventional algorithms are Wi-Fi, trilateration algorithm, and fingerprint algorithm. So we use an idea to combine these both position result. So the main problem of trilateration algorithm is they use the free space path estimation model. So when the channel condition change, the result reflects or degrade our performance. And the fingerprint also depends on the data side, how much data we have. There is no that only this system perform. So our idea is to combine both and improve the position result. So here is the basic trilateration approach we use for access point, and we estimated the XP and YP is our user position using this equation. And basic fingerprint approach. So using fingerprint approach, we first collect the RSSI data and we create a fingerprint database. That is called offline phase. And in online phase, again we use the RSSI values and we use any of these algorithms like NN or KNN or WKNN Bayesian approach. Any of these algorithms, we estimate we estimate the equilibrium distance, and we compare the RSSI values and estimate the user position. So to combine both algorithm result, we used again a Kalman filter based algorithm, linear Kalman filter. And also for the experiment scenario, the same experiment we consider access point in the both rectangular and straight line motion. So here is our estimated result, like from using proposed Wi-Fi fusion, and also we consider a conventional approach weighted path loss model, and also the fingerprint approach and trilateration algorithm for rectangular and straight line motion. Here is the average localization error for rectangular motion in 4 scenarios, and also the next straight line motion from the 4 approaches, our proposed approach and the other conventional approaches, we estimated the average localization error. So here is the probability distribution comparison for both approaches in straight line motion and rectangular motion. So finally we summarized all our results. So our proposed Wi-Fi fusion system achieved better mean localization error as compared to other conventional approaches in both scenarios, rectangular motion and straight line motion. Here is a small demonstration video. The system is not very accurate, or the system is useful in a limited context, and processing RSSI signal takes some time and delay, and the fluctuation is RSSI also in real time not give very accurate result. So the user movement is also not very flexible. The user is also limited when we consider the RSSI data. So when we consider RSSI based localization, the RSSI signal fluctuation, multipath effect, signal interference, or channel behavior model, and sensitivity to channel inconsistency and computation complexity. So to reduce these all challenges, we combine our IME sensor data with the RSSI data. So here is our proposed sensor fusion framework. So the upper part is our previously proposed IME based localization, and the down part is the proposed Wi-Fi based localization approach. And we also use the same experiment scenario, rectangular motion and straight line motion, and estimated did a comparison with the proposed sensor fusion framework with some conventional approaches. So here is the estimated average localization error for both scenarios, and also probability distribution of localization error, and summarized our proposed sensor fusion framework analysis as compared to some other approaches. Our proposed approach gives very accurate result in both rectangular and straight line motion. So when we use the sensor fusion framework, the first major issue is computational complexity and data inconsistency, and installation maintenance cost of Wi-Fi based localization, and issues with the real-time implementation. When we use RSSI signal, the real-time system is not very accurate. So we check the possibility of camera sensor for localization, or just normal smartphone camera. So here is our proposed camera-based indoor localization system. So the upper part is our previously proposed IME sensor, and the down part is our camera-based localization. So finally we combined both position results together to get a very accurate result. So for the fusion, we used our Kalman filter, same previously implemented Kalman filters with different state metrics, and these are the basic Kalman filter predicting and updating algorithm. And for the experiment, we used Samsung old model. This is due to the processing delay. So if you record with the new smartphones, the 40 video or something, the processing delay is very high. So we use our old Samsung model, and this is our external IME sensor. To reduce the computation complexity, like if you use the smartphone IME sensor and camera together, so it will be problem for the data collection. So to validate that, we used an external IME sensor, and here is our experiment area. So the user moved surrounded by this cable. So here is our position estimation using IME sensor, and for the camera-based system, we consider ORB SLAM localization and UCO SLAM localization. So ORB is the most common and famous camera-based localization approach, and the UCO SLAM is the recent research. They use some ARCO markers in the experiment area. Here we mark the ARCO marker. So using these markers, we estimated the camera pose. So directly we can estimate the user position. So when we combine both results, like the ORB SLAM plus IME result and also UCO SLAM plus IME result, our performance improved as compared to individual system. So here is the result. So our proposed hybrid localization system using UCO SLAM plus IMU, we have 0.06 or 6 centimeter localization error as compared to other approaches. So here we also estimated, to claim our proposed approach, we estimated the average localization error and also probability distribution of localization error. And here is a demonstration video about ORB SLAM localization using ORB SLAM. Due to the video picture, like small delay is there. So here we track the camera pose, using ORB-SLAM algorithm. And next, we used some markers in the experiment area and we estimated the user position. So here is the user position. So when we use the camera-based localization, first major concern is user privacy. So we can't install camera in everywhere. For example, the toilet or some other privacy places we can't install. And also installation cost and processing delay and camera motion speed also affect the performance of the system. So to provide a centimeter level very accurate localization system, we use the UWB based localization. So here is the proposed UWB localization system using deep learning. So here we simulated the entire UWB system in MATLAB and we estimated the user, the distance information from each anchor to the tag, and we introduced the deep learning architecture, LSTM model, and we trained the model with the user distance information and we estimated the user position. So here is our proposed LSTM model for localization. We use the deep LSTM layers and our number of data samples 2582 and training data, we split the data training and testing, and the output of the number of input neurons are three distance values from each angles. We use 3 angles, and the number of output neurons is 2 different, like x and y position. So the output of the deep learning architecture predicts the user x and y positions. So here is the forward propagation of LSTM, basic LSTM unit, and here is our LSTM parameter values, like the ratio of training data to overall data 0.75, number of epochs we consider 100, batch size 5, time step 30, and hidden nodes 256, and random optimizer and mean square error, loss function, and block rate 0.2. To reach this parameter values or to define this parameter value, we did many simulation or hyperparameter tuning with the localization accuracy for training data with a different learning rate. So using this result, we identify the best learning rate and also a different optimizer. We also consider different types of optimizer, atom optimizer, SGD. From there, we analyze which optimizer gives the best performance. So we fix that, or we pick that optimizer as our localization, fully our localization. And also we use the performance of different loss functions. And also we did hyperparameter tuning for batch size, number of hidden nodes, and time steps for different values. And finally we estimate the optimal values for our data for training. And here is the LSTM based localization. So we start with our distance information from the language to the tag, and a regression model based LSTM. The LSTM uses as a regression model, like a predicting user x and y position. So collect the distance values from the trajectory and move the user in the trajectory and repeat the experiment to get a amount of data is sufficient for our experiment, and generate the distance database in each time slot and initialize the structure of LSTM and train the LSTM model with the again collect the data, distance data for testing and verify the LSTM model and change the parameter and continue this process to get a optimal value. So number of LSTM layer and mean localization error we did comparison, and from here we found the number of LSTM 2 is the best for our approach. When the number of LSTM layer increases, there stands for the hyperparameter. When it increases, the localization error is also affecting. I mean, not that much changes, is localization error is increasing. Overfitting, basically it will be overfitting. And when we use the training time, testing time, we also compare with our proposed LSTM approach with some basic deep learning architecture like backpropagation, extreme learning machine, and RNN values. So our approach has higher time or training time as compared to other approaches. But when we consider the localization error, that training time is reasonable for our application. So we also consider the different number of angles change from 3 to 5, and also we analyzed with some different models, backpropagation, extreme learning machine, LSTM, RNN, and some conventional approaches, FP, fingerprint or linear least square estimation or maximum likelihood estimation or weighted centroid estimation. So our LSTM based approach shows best performance as compared to all other conventional approaches. So in the conclusion, first we proposed a IMU sensor-based localization system and we implemented a real-time system. And to reduce the errors, we introduced the Wi-Fi RSSI signals to the system. And also to get a very accurate result, we combined both RSSI and IMU sensor data together to get a very accurate result. And to solve some indoor channel characteristics problem or some challenges, indoor localization challenges, we introduced the camera sensor, and camera-based localization system gives very accurate result. But even that system has some serious issues. So to get a very accurate and advanced localization system in scientific level, we use the UWB signals as our localization, and we have very accurate result. Thank you for the.